All right. Hey, everybody. Today, we're going to continue looking at curves in three-dimensional space, and we're going to develop the theory and the tools that we need to describe how these curves are sort of curving about and twisting in R3. Now, as a reminder, when we did this for planar curves, so curves in R2, the key idea was that of the curvature function, which in a very real sense described just how our curve curved in the plane. As you might expect, though, in three-dimensional space, having more directions to go in, describing how our curve is twisting about becomes a little more complicated. And what we'll see is that we ultimately need two functions, the curvature function and the torsion function, to describe how our curve is twisting about. So we're going to jump into this. I'm going to start with a definition, which we'll justify in just a moment. So we're going to be given a parametrized curve, and let's assume that this curve is regular and is C2, so we can take derivatives of it, at least two derivatives of it nicely. So given such a parametrized curve, x, and we are given with that the associated Frenet frame, which we discussed last time, and that's the tangent normal vector, the unit tangent vector, the principal unit normal vector, and then the unit binormal vector. So given that Frenet frame, the curvature function, kappa, is going to be defined as follows. Kappa of t will measure, at any given time t, the length of our unit tangent vector t prime, I should say the length of the derivative of our unit tangent vector, so the length of t prime, divided by the speed of our curve s prime. All right, now intuitively, right, this is going to measure how quickly our curve is curving about in space, much as our curvature function in R2 did. Notice t prime is describing how fast, or I should say t prime is describing the change of our unit tangent vector. By taking the norm of that, by measuring the length of it, we're in a sense measuring the speed of t, right? So we're measuring how fast t is sort of flipping around. And then when we divide by s prime, divide by the speed of the curve, we're normalizing this across reparameterization. So we will get a function that measures how quickly our curve is curving. All right, a few small notes about this definition and about our new function kappa. First of all, notationally, we will use just kappa now as opposed to kappa sub g. Right? So kappa of t will describe the curvature in three-dimensional space, while kappa sub g is the function that describes the curvature of a curve in two-dimensional space. Secondly, by using this definition of curvature, we get an identity that is exactly the same as our identity for curvature in R2. Specifically, we get this equation, that t prime as a vector will equal kappa times the speed times our, in this case, principal normal vector p. Remember, in R2, we had the same equation, but with our unit normal vector, which we called u back then. So this is the exact same equation that we had for kappa back in R2, suggesting that these functions play similar roles. However, interestingly, in this case, or in the case in R3, kappa is non-negative, meaning that for any given parameter input t, kappa of t is greater than or equal to 0. Right? And we can see that from the definition. If we assume we have a regular curve, we assume that the speed is always positive. So this is always positive, and this length is always going to be greater than or equal to 0. And so kappa will also be greater than or equal to 0. So a small way in which our curvature function in this new setting differs from that in our previous setting. But otherwise, it's pretty much the same. So as we sort of saw, kappa is going to be measuring t prime, right? Coming back up here to our Frenet frame, we have these three vectors. Kappa is really the one that's telling us how t is changing, right? It's really the one that measures, in a certain sense, what t prime is. And so that will describe how our unit tangent vector is changing in time. But we also have these two other vectors, p and b, and we might be interested in how they change in time as well. And by examining those, specifically by examining b and trying to find b prime, we will really see where this extra function, the so-called torsion function, will come from. And so let's explore that. our goal is to determine how B changes, or in other words, our goal is to really to measure something meaningful about B prime, right? And now to do this, we are going to start with the definition of B, right? And remember, B was just defined to be T cross P. That's how we defined it in our last video. And then we're going to take the derivative of this and see what we can derive. Now there's a few ingredients that will help us along the way. So ingredients in our argument include the following, right? First, that if we take the derivative of a cross product, it obeys a certain kind of product rule. Second, if we have two vectors that are pointing in the same direction, right? So they're parallel vectors, aka one is a scalar multiple of the other, right? So if they're parallel vectors, that means that V is really nothing more than some scalar times W. Then their cross product will equal the 0 vector. And then third, that if we are given an orthonormal basis, or really any basis of R3, a vector can be uniquely decomposed into a linear combination of these basis vectors. We saw this previously in seeing how any vector could be written as a linear combination of our standard vectors I, J, and K. But we'll actually be using this today in describing how a vector can be decomposed into a linear combination of the Frenet frame vectors, and more on that in a little bit. But these are our three big ingredients in the short term, and with that in mind, let's see how we can calculate B prime. All right, so when we calculate B prime, first, as we saw, we have a tangent, we have a product rule here. So we will get T prime of T cross P of T plus T cross P prime, right? And these are all functions of T. I'm just not writing the T's right now to keep this looking a little cleaner. Let's see what we can do from this. T prime, as we saw before, right? T prime is really equal to kappa times S prime times P. So this whole expression is really some, what's the word I'm looking for? Some scalar multiple of P cross P. In other words, this vector and this vector are parallel to each other, and so this whole piece is going to be equal to 0. So we really get that B prime is really equal to T cross P prime. And then our goal is going to be, how can we rewrite that in a meaningful way? So currently, B prime is equal to T cross P prime. And we run into some trouble because we don't actually know what P prime is at the moment, right? Much like we don't know what B prime is, we don't know what P prime is. So let's take a moment to look at P prime, right? So maybe sort of as an aside here, P prime is some vector. This is at P prime of T again, right? This is some vector in three-dimensional space. I don't know exactly what it is, but because it is a vector in R3, and because I have my Frenet frame, an orthonormal basis of R3, I can write P prime as some linear combination of T, P, and B. I can write it as a linear combination of these three vectors. So this will be some number times T of T plus some other number times P of T plus some third number, just move that over a little further, some other number times B of T. All right, and now the question is, what are these coefficients out front? What are A, B, and C? First big clue, this piece is actually going to be 0, right? And the reason for that, that's going to be 0, and the reason for that is because P prime, right, is actually perpendicular to P, right? All of these unit vectors, right, these vectors of unit length moving along the curve, are perpendicular to their derivatives, as we've seen. So because P prime is perpendicular to P, that means that p prime does not point in the direction of p whatsoever. That coefficient has to be 0. And so we're left with this slightly simpler version. P prime equals a times t plus c times b. And so this is going to be the expression that we sub back in over here. Right, so we're going to take that and plug it back in for p prime over on the left-hand side. So what does that mean? Coming back down here, we have b prime equals t, fix that, t cross, and now in parentheses, it's this expression with unknown coefficients, a t cross c b. All right, and by our properties of cross product, this should be make sure that's clear, that's some vector addition right there. By properties of cross product and cross product distribution, we now have, this will become t cross at plus t cross cb. But what do we know about each of these, right? Again, going off of properties of cross products, AT is parallel to T. They point in the same direction. And so this will, again, just be a 0. And this over here, right, this will equal, we can factor out that scalar multiple, so that's C times T cross B. And what's T cross B? Well, according to our Frenet frame, T cross B will exactly equal negative P. So this will become negative C times P. And so what do we get at the end here? Well, once all the dust has settled, we end up with the equation that the derivative of our binormal vector B is equal to some scalar multiple, negative C, right? So, but some scalar multiple of P. And so B prime is pointing in the same direction, I guess a parallel direction, technically perhaps an opposite direction, but a parallel direction to our vector P. And this allows us to motivate the following definition of the torsion function. The torsion function will be a factor of this C once we have accounted for speed, as we often do, right? So again, if we take a regular C2 curve x, the torsion function, which I'll denote using the letter tau, will be the unique function so that B prime is equal to negative S prime times tau times P, where what we have here is that this piece, the S prime times tau, is really our coefficient C from before. Right, so we've used that C, and then after we account for speed, what we have left, that extra factor, is how we define our torsion function. Now, much like our original curvature function, right, this is defined implicitly because it's defined as an equation that, or as a function that makes this equation hold true. But through the derivation we've just gone through, we see that such a function must exist and must be unique. Now, this is kind of cool. It gives us two different functions, right? Curvature and torsion, kappa and tau. They're both describing how our curve is moving through space, but one of them is focused primarily on T prime, right? While the other is focused primarily on B prime. So curvature, which focuses on T prime, tells us how our unit tangent vector is sort of curling around in space. It measures the magnitude of that in a certain sense. And so curvature, at least intuitively, measures how much our function x curves. While torsion, right? Torsion has this binormal vector. So maybe if my curve is sort of flowing up this way, my binormal is pointing, sort of in a normal direction. But torsion is measuring how that curves around or how that twists, right? So again, in a loose, intuitive way, these are each measuring how our curve goes through space, but curvature is measuring how our curve sort of curves, while torsion is more measuring how our curve twists as we go through three-dimensional space. All right. And so here's our slightly incomplete picture at the moment. We've calculated our t prime as being s prime times kappa times p. We've calculated our b prime as being negative s prime times tau times p. And there's this question of, can we calculate p prime? And does that give us a new kind of function, right? Maybe there's not curvature or torsion, but some other, function describing the twistiness of p. And it turns out the answer is no. If we calculate p prime, I should really say p prime right here. If we calculate p prime, what we will get is actually another function that's only built out of curvatures and taus. Specifically, what we get is that p prime is going to equal negative s prime times kappa times unit tangent vector plus s prime times tau times the binormal vector. Right? And in particular, once I know my curvature function and my tau function, I can describe t prime, b prime, and now p prime, all in terms of curvature and torsion. And so as a result, those two really are the two fundamental functions for describing how my Frenet frame, and then by extension, my curve, move about in space. So I want to conclude this video by writing these equations in a slightly different form, sort of a matrix/vector form. And it's going to come from the recollection, well, let's just go down there. So we want to first remember, right, or recall that each of our vectors, t, p, and b, can be written using vector notation as these column vectors of length 3. Right? So our t is going to be t1, t2, t3 for appropriate numbers. P is equal to p1, p2, p3, and b is equal to b1, b2, b3. Right? Now, of course, this is all part of our parametrized curve x of t. And so all three of these, right, all three of these vectors are really functions of time. Right? So this is like t of t, p of t, and b of t. And then by extension, each of these 9 entries are themselves sort of regular scalar functions of time. So I won't write them all, but write t1 of t, t2 of t, t3 of t, and you get the picture. p1, p2, p3 of time, b1, b2, b3 of time. So with that in mind, we can define a matrix, which I'll just call for the moment matrix M, to be the 3x3 matrix that is these 3 vectors all stacked next to each other. So I can write that as TPB, or in this 3x3 form, right? Again, all 9 of these entries are functions of time, and at any given time t, this is just a matrix, right? So it turns out that the information above describing t prime, p prime, and b prime can be used or rewritten in this nice matrix form, right? And so specifically, we get that the derivative of each of these entries, which I've just written as d dt of the matrix, or I'll write now as m prime, is equal to, well, we have this scalar multiple out front, that's our s prime, right? That was a common factor in every single one of our derivatives, so we have s prime, times our original matrix M, times this vector, this matrix right here, right? And this is this matrix with all zeros along the diagonals, and then kappa, negative tau, and tau in these entries. And I'll just call this matrix A. So we can write our series of differential equations, or our sequence, system of differential equations, from up here, describing the derivatives of t, p, and b in this sort of slick way here, where m prime is equal to s prime times, and then in matrix multiplication, m times a.